Section 4.2, we're going to look at experiments, and there's a lot of vocab in here, so we got to make sure that we have these words down, okay? An observational study is when we are just looking at things that have already occurred in the real world and not trying to attempt to influence it. So this study looked at patient medical records and just looked at their level of vitamin D and whether or not that person had diabetes. Okay, so that is an observational study. They weren't applying any sort of treatment. They weren't telling people to take vitamin D. They were just observing whether or not they did. Okay, a response variable is the measure of the outcome. So in this case, we're talking about, did that person have diabetes? Yes or no? That is the response variable that we are measuring. And the explanatory variable is what we think causes the change in the response variable. So in science terms, this would be your dependent variable, okay? Their vitamin D concentration, we're hypothesizing that that is affecting whether or not the person has diabetes. Okay. The problem with observational studies is it's very difficult for us to say that vitamin D is the cause of the lower risk of diabetes. Because if we looked at those groups that they came up with, the people with the high vitamin D also had a better diet, they exercised more, they were more likely to take other vitamins. Okay, so because these other variables are at play, we can't say for sure that it was just the vitamin D that had the effect on the diabetes. Okay, and this is called confounding. All right, when we have some other things in the way, and we can't say for sure that it was just the explanatory variable that we're trying to test. Okay, when you are asked to explain confounding, all right, just like when you're asked to explain bias, there's two things we got to say. Okay, how is that confounding variable? So in this case, let's say like exercise, right? Exercise was one of the things that was also different. How is exercise associated with the explanatory variable of vitamin D, and how is exercise associated with the response variable of having diabetes? Okay, so people who exercise outside a lot have higher concentrations of vitamin D. All right, and then if we say that people who exercise a lot are also less likely to get diabetes, then exercise and vitamin D are confounded. We don't know which one is actually affecting whether or not people have diabetes, or if it's both of them. Okay. Something that we can do to try and address confounding is we can, instead of an observational study, we can perform an experiment. Okay, so this is where we are deliberately imposing a treatment on the people in our study. So in this case, they found 500 people and they actually gave some of them vitamin D and said, take this. And then the other half did not get vitamin D to see if there was a difference between the two groups. Okay. Only experiments can be used to determine cause and effect. Okay, so does vitamin D cause the risk of diabetes to be lower? The only way we can do that is through an experiment. Observational studies don't give us enough information because of potential confounding. All right. Here we have, I want you to read real quick through this study on malaria, and we're going to talk about some experiment vocabulary. All right, so treatment is the thing that we are specifically applying in the experiment. So in this case of malaria, they split the kids into two groups. They either get regular screenings and follow-up treatments, that's one, or they get no regular screening. Those are the two treatments in this experiment. Okay, experimental units, aka subjects. Okay, so in this case, it would be the schools. All right, it could be people, it could be animals, it could be things, just depends on the nature of our experiment. Okay. Sometimes we have more than one explanatory variable. Sometimes we have different levels of that explanatory variable that we are looking at. So like in the vitamin D pill, we could give them like a 200 milligram pill, a 500 milligram pill, something like that. Okay, so here we have an example where we're testing the 5-second rule. We got different foods, we got different surfaces, we got different amounts of time, we got all kinds of things going on. So what are the different factors in this experiment? Type of food, and there's 4 levels because there's 4 different types of food. Type of surface, they choose 4 different surfaces. The amount of time that the food is left on the surface, again, there were 4 different time periods. And then the method of bacterial prep, what they put on the food before doing the experiment. All right, so there's lots of different factors in this experiment. Typically, we're only looking at 1 or 2. This one is a little extreme, but it's just to help you figure out what different levels of something could look like. Okay, when we design experiments, things that we need. One is comparison. We always want to have 2 or more treatments. All right. We do not want to give everybody the same treatment because then we have nothing to compare it to. All right, so we've got patients that we're going to try and treat their pain with magnets. Okay, some of the magnets are active and some of them are inactive. So those are our 2 treatments, and we're going to compare one to the other. All right, this is the use of a control group. All right, so the control group is the one that doesn't get a treatment at all. Sometimes they are given a placebo, which in this case, like a fake magnet. All right, so that we can compare the results. So we want everything to be the same as much as possible, except for the thing we're actually testing, which in this case is the magnet. Okay, that's how we know it's the magnet that's actually causing the difference and not something else. Right? The reason that we use fake magnets instead of just not giving them anything is because something called the placebo effect, which is sometimes if you give people some sort of treatment, they're like, yeah, that helped me. It kind of just messes with their mind a little bit. All right. So one thing we do to help counteract this is we can make our experiments blind, meaning the person doesn't know what they're getting. So the people in this experiment did not know if they had a real magnet or a fake magnet. Okay. In a double blind experiment, anyone that interacts with that person also doesn't know. So like if the person rubbing the magnet on their knee doesn't know whether it's real or fake, that's a double blind experiment. Okay, single blind would be one group doesn't know. So either the subjects don't know or like the people, the experimenters that talk to them don't know. All right. Second principle of experimental design, random assignment. All right, the purpose of random assignment is so that our groups are roughly equal. Okay, we could have all kinds of differences in our group, male, female, age, genetics, all kinds of things. So if we randomly assign them, that's going to give us the best chance of having those groups be kind of equally spread out. Okay. We can use the same methods of random assignment that we did for simple random samples. Okay, so we could use slips of paper, hat method. We could use technology. We could use, it says table D here. That's a table of random digits. All right, so example of what that would look like. All right, with a piece of paper, it's going to be very similar to what we just did last lesson. All right, so we write 25 A's, 25 B's, make sure the slips of paper are the same, shuffle them all up, all right, and then hand them out. Anybody who's an A gets an active magnet. Anybody who's a B gets an inactive magnet. Okay. If we were going to use technology, again, same rules as last time. We got a label. So label each patient from 1 to 50 and then randomly generate 25 different or unique numbers from 1 to 50. All right. The first 25 get active. The second 25 get inactive. Okay, and then in table D, the table of random digits, it would be the same sort of thing. We'd have to label each patient. This time we got to do 0, 1 to 50 because we have 2-digit numbers. All right, and then the first 25 unique numbers get the magnets. Everybody else is the inactive magnets. Okay. Third principle is we have to have control. All right, and control in the case of a statistical experiment means keeping as much the same as possible so that the only difference between the 2 groups is the actual treatment we are applying. Okay. So in this magnet experiment, they used the same scale, right? We told them 0 to 10 or whatever it was. We didn't let them kind of just use their own words to describe the pain. Everybody received the same amount of treatment. Everybody got 45 minutes. All right, keeping those things the same so that as much as possible, the only difference was the magnets. And our fourth principle is something called replication. This just means each group needs to be large enough that any sort of outliers or messy things in our group don't skew the results too far. Okay. Make sure we don't get confused with the English definition of replication, meaning like just repeating it. Okay. In statistics, it has a very specific meaning, which just means that we have enough experimental units in our study that we can be confident in the results. Okay. Different ways that we can do experimental design. Okay, there's a couple different methods that we can look at. And a completely random design, this is kind of similar to our simple random sample. Everything is just random. So we have our people, we just split them up into two groups completely randomly, and then they get two different treatments, and we compare the results. Okay, we can also do what's called a randomized block design. And this is kind of similar to like a stratified sample. So a block would be anything that we think might affect the results. So if we're testing this medicine and we feel like it might affect males differently than females, right? We might block by male and female. And then within each block, we would randomly assign to treatments. All right, so we would do like all the males and split them into two different, or all the females. The example they use here is we have a popcorn lover and she's got 4 different varieties of popcorn: butter, cheese, natural, kettle corn. Okay, we're going to test it between the popcorn button or the amount of time. All right, it might be smart to block by kind of popcorn here. Okay, so split the butter evenly, split the cheese evenly, split the natural evenly, so that type of popcorn does not become a confounding variable in our study. We can also do what's called a matched pairs design. And in that case, things are paired up. So we can do it one of two ways. We can have similar people or similar experimental units. A lot of times they'll do these studies like with identical twins, and they are paired up and each twin gets like one treatment. All right, so they get opposite treatments and we compare the twins. Another way they can do it is each unit gets both treatments and then we randomize the order. So that an example of that is like this. We want to know if adding a fuel additive can increase fuel efficiency. And we have 20 cars. So if we wanted to do a matched pairs design here, what we would do is each car would, drive with the fuel additive and then without the fuel additive. And we would randomize the order, whether they did it with or without first. And then each car is compared to itself. So what was your miles per gallon with the additive? What was it without? Just that car to itself. That way the differences between cars don't affect the results. All right, and that is it for experimental design.